Welcome to this explainer. Today, we're going to demystify the somewhat intimidating world of IPsec. You know, if you've ever found yourself staring at a router prompt, totally lost in the technical weeds of VPN configurations, wondering why on earth Phase 2 just won't come up, well, you are definitely in the right place. We're going to bridge that frustrating gap between universal RFC standards and how things actually work in the real world. Specifically, we'll be looking at how industry heavyweights like Cisco, Palo Alto, and Juniper handle these exact protocols. So let's jump right in. IPsec is basically an absolute alphabet soup of acronyms. So here's our quick roadmap. We'll decode the fundamentals, unpack those IKE phases, compare how different vendors twist the rules, and finally do a deep dive straight into the command line. All right, Section 1, Decoding IPsec Fundamentals. Let's establish the ground truth that actually makes secure internet communications possible. At its core, you have to remember that IPsec isn't just one single protocol. It's an entire foundational suite of protocols used to spin up virtual private networks. Whether you're configuring a massive gateway-to-gateway connection between two corporate HQs or just a simple host-to-gateway setup for a remote worker, IPsec is the engine. And the fuel for that engine? That would be security associations, or SAs. These SAs are uniquely defined by specific parameters like your Security Parameters Indexed, the SPI, and the destination IP address. This is what guarantees every single packet knows exactly where it's headed and precisely how it's protected. Now, looking at this breakdown, notice how an IPsec collection isn't just one big two-way pipe. It actually demands separate security associations for outbound and inbound traffic. It's a pair of one-way streets, and those databases you see there, the Security Policy Database and the SA database, that's what your router relies on to decide if an incoming IP packet even needs processing and which unique connection parameters to apply to it. Honestly, it's a lot like a very strict bouncer checking a highly specific cryptographic guest list before letting any data through the door. When you're spinning up these connections, choosing your protocol carefully is an absolute must. You've got to know the difference between AH and ESP. The authentication header, which was defined way back in RFC 2402, practically ancient history in internet years, is fantastic for strictly preventing tampering and ensuring data integrity. But, and this is a massive but, it gives you zero payload encryption, none. If you actually want your data payload locked down and unreadable to anyone snooping around, you have to use the encapsulating security payload, or ESP. That's what delivers that crucial encryption right alongside the integrity. Okay, Section 2, Unpacking the IKE phases. We know what secures the data, so let's look at how these devices actually introduce themselves and set the ground rules. So IPsec leans heavily on the Internet Key Exchange, or IKE, to establish shared symmetric keys. Think of IKE Phase 1 like two suspicious parties verifying their identities in a secure, locked room before shaking hands. They'll either use main mode, which is a bit slower but entirely protects their identities, or aggressive mode, which speeds things up but exchanges some info in the clear. Once they mutually authenticate and form that initial SA, boom, they move to Step 2. IKE Phase 2 is where they actually build the secure pipeline for the data. Operating in quick mode, they negotiate the exact AH or ESP algorithms we were just talking about. Section 3, Comparing Vendor Implementations. With all that academic theory out of the way, let's pivot and see how hardware vendors actually interpret these RFC standards in the wild. This breakdown right here is exactly why network engineers have to be so adaptable. The RFCs are just blueprints. Every vendor builds the house a little differently. Cisco, for example, loves clinging to legacy terminology like ISAKMP for IK, and traditionally relies on a crypto map approach to tie IPsec directly to physical interfaces. Then you have Palo Alto, a next-gen firewall which abstracts a ton of this into slick GUI-driven profiles, but then strictly mandates that Phase 2 operates only in quick mode. Meanwhile, Juniper takes a totally different route. They use a highly hierarchical, route-based approach and put their foot down by forcing all IPsec connections to operate exclusively in tunnel mode. It is literally the same underlying math, just spoken in a completely different dialect. We've talked a lot about the algorithms, the phases, and those vendor quirks, but it really begs the question, how does a network engineer actually type all this into a router? How do we take the pure theory of IKE Phase 1 and 2 and make it operational? That brings us to Section 4, our Juniper Configuration Deep Dive. Let's pull up the command line and break this down step by step so we aren't just staring at a blinding wall of text. So unlike Cisco's older flat crypto map style, Juniper uses a super modular, almost Lego block style hierarchy. You don't just blast in one long, messy command. First, you define your IKE proposals. That's where you specify your exact encryption algorithms and keys. Then you bundle those proposals up into IKE policies. Finally, you attach those policies to an IKE gateway, which manages the physical endpoints and handles the certificate authorities. And guess what? Phase 2 works the exact same modular way using specific IPsec proposals. Once you wrap your head around it, it's a beautifully logical flow. Check out Phase 1 in action right here. We are explicitly defining our IKE proposal, creatively named IKE-prop. Notice how the Diffie-Hellman group is locked into group 2. Our authentication algorithm is set as SHA-256, and we're rocking the robust AES-256 CBC for encryption. This right here, this is the direct translation of that abstract theory into real, tangible action. And the next step is where it all comes together. Once you create that proposal, it just kind of sits there, doing nothing until you actually use it. To build out the hierarchy, you bind those exact security parameters directly into the active IK policy using one brilliantly simple set command. You literally just tell the router to attach proposals IK-prop. It is modular networking at its absolute finest. But wait, after all that heavy cryptography is sorted in Phase 1 and Phase 2, you still have to tell the router what to do with the actual data packets. You map the tunnel to reality by creating strict security zones. Just look at the specific policies being configured here to filter exactly which traffic is allowed to flow from your cozy internal trust zone out into the encrypted VPN zone and back again. It acts as the final gatekeeper for your secure data. All right, so we've perfectly configured our AES-256 encryption, our DH groups are solid, our zones are active, everything's great, right? Well, a massive disruption is looming on the horizon for all of us in networking. With the insane pace of technological advancement, what actually happens when standard cryptography simply isn't secure enough anymore? This is where things get incredibly futuristic. Juniper is already laying the groundwork for the quantum computing era right now. By configuring post-quantum pre-shared key, or PPK, profiles, these routers can actually reach out and fetch quantum key distribution keys from an external server. By just referencing this futuristic key profile under your IK gateway, you take a standard, traditional IPsec tunnel and instantly upgrade it to be entirely quantum safe. We've covered a massive amount of ground today. From the absolute basics of SSAs and ESP, all the way through the intricate configuration quirks of Cisco, Palo Alto, and Juniper, right up to the bleeding edge of quantum cryptography. So, as you take this knowledge and bridge it from theory to practice today, I want to leave you with one final critical thought. Honestly ask yourself, is your current network infrastructure really prepared for the quantum threats of tomorrow? Thanks so much for joining me on this explainer, and keep building secure networks.